Welcome. In this video, we will start discussing so-called martingales. So far we mainly discussed the Brownian motion and some of the properties, in particular the properties of its natural filtration. And now we would like to move on to a bit more general class of stochastic processes, which I want to introduce now. And these are the so-called martingales. So I hope you might have seen martingales, at least in discrete time already. Let me directly start by giving you what a martingale is and some variations of it. This is definition 2.8. So what I want to consider is a stochastic process denoted by x, as usually indexed by time. And I want that this process is first real valued, right? And ft adapted stochastic process. So what is an end? So we assume that that there is an underlying filtered probability space. So there's a probability space with a filtration on which everything lives. Probability space with filtration. Okay. And now we want to consider that's a real value stochastic process, which is assumed is adapted to some filtration. And we want that this stochastic process is also integrable at any time. So if I look at the expected values of the absolute value of the process at time t, this is a finite number for all t. Okay, so this is my given stochastic process. And now I call this stochastic process x is called martingale or ft martingale if we have this condition that it's a fair game. Okay, so the conditional expectation of x given xt given the filtration up to time s or at time s is exactly equal to s. No? That's what I want to call a martingale. Okay. Right. And well, there are some modifications of martingales, which are so-called super martingales, which I also would like to introduce. So a sub-martingale is if this equality relation is replaced by the filtration, that the conditional expectation of xt given fs is greater or equal than xs. So the super-martingale system basically a game in favor for us. So if I'm at time s, my expected value given the information up to time s is that for example, if x moles a payoff, it gets higher. And then they're the same. I mean, the other inequalities leads us to super martingales, right? Yeah. if we now replace here in the Martingale definition the equality by an inequality, but now in the other direction. So if we are at time s, we expect that the expected payoff at time t is less than the payoff at time s. And of course, this has to hold for all s t in our interval 0 to t, and we have to assume that s is less or equal than t. Okay, so these are what I want to also introduce. So there are variants of it, like super and sub martingales. Which also. Okay, before we're going on some remark. So two remarks, right? So if we see a stochastic process and you want to verify that it's a martingale, you have to check three things, right? You have to check that it's adapted, that's integrable, and that this conditional expectation is equal to the current time value. Okay, so the martingale, there in this definition, there are three properties hidden which characterize actually what a martingale is. And another remark is, so I will often not use here this FT martingale to just say martingale. If I just say martingale, either it's clear which filtration I supposed to consider, or if I just consider the natural filtration generated by the process X, right? So if I take the natural filtration of the process X, of course, X is adapted to its own natural filtration. So there's nothing to do. And then one needs only to check the integrability and this martingale condition here. Okay, let me come to three examples, which you will also study or have studied on the problem sheets. So you can verify yourself that the following three processes, which I'm going to give you, are indeed martingales. So what I want to start with, I consider a Brownian motion because this is the process we know best by now. It's a Brownian motion, and I assume that the filtration is it's completed natural filtration. Okay. So the filtration generated by the Brownian motion, and then I put in all the null sets to have a completed filtration. And in particular, then I have a right continuous filtration, as we learned in the last video. Okay. The following processes are martingales. Okay, so the first thing which follows by the simple Markov property is if I look at x1 just given to be the Brownian motion. So the Brownian motion itself is a martingale. Okay. Second process is I take the Brownian motion to the power 2. And then I subtract t. This is again a martingale. And you can check that if you only look at, if you drop this minus t term here, you only have a submartingale. And the last thing is what's called geometric Brownian motion of Lex-Gold's model. So we will come back to this example at the end, or the second half of the lecture, of course, again. So if you look at the exponential of, for example, sigma times the Brownian motion at time t, and then minus sigma squared divided by 2 multiplied with t, and you can do this for all sigma. This is again a martingale. Of course, here t is always between 0 and t. Right? So this give you three stochastic processes, which you can all verify on yourself that they are indeed martingales. Okay. And now I would like characterize basically what are martingales, or what a martingale is in terms of stopping times. And before doing this, let me recall again what a stopping time is and what is the sigma algebra of the tau path. So tau is the stopping time. Okay. Here we go. Definition. It's 2.10. Okay. So I have my filtration as before. Random variable tau, right, maps from our sample space omega t, or in the interval 0 to t, and now we stopping times we allow to take the value infinity. It's okay. This just means we are never stop. Is called ft. Right, the stopping times are with respect to a filtration stopping time. If I can decide at time t, so if tau is less or equal than t, I can decide based on the information given of nft. Well, t in 0 t. So I'm not allowed to use any information of the future when I want to decide to stop or not. So what the value of tau is determined just by the information up to time t, right? So I can decide at time t whether tau is less or bigger than t based on the information at time t. Okay. And if I have now such a stopping time, I can define a sigma algebra of tau past find as this is tau f tau, which is given by all the events A in my underlying sigma algebra F, such that it contains all the information I have given tau up to time t. So up to time tau. So, right, so formally this means if I take the set A, I want that if I intersect it with the event tau is less or equal than t, is ft measurable for all t. And if you want to check yourself, so if you set t, so here at the tau equal to t, this means this is just the sigma algebra at time t. Okay, so this is okay. All right. So these are two definitions, which we will recall them also in the tutorials. And well, I hope you have seen them at some point. All right, so let me come to the promised characterization, which is will be the main theorem. Oh no, the main work of this in this video. This theorem 2.11. So what is my setting? I consider for filtration as before, and I take a right continuous process, right? So the right continuous, if you may recall, is that my sample part of the process X are right continuous, right? continuous stochastic process. And then I have the following equivalent formulation. Following statements are equivalent. Okay, what's the first one? First one is that X is an FT martingale. Right, so this is actually what we want to equivalently characterize. The second one is for all bounded FT stopping times, tau, we have that the process stopped at time tau, so x tau is in L1, and the expected value of x tau is always given by the expected value of x0. Okay, the third formulation, which is often referred to as optimal, optional sampling, tells you what for all stopping times, so bounded stopping times, sigma and tau, where I want to assume that sigma is less or equal than tau, we have that again x tau is in L1, and the conditional expectation of x tau given the sigma algebra at time sigma, so the sigma algebra of the sigma parse, is equal to x evaluated at sigma. Okay. And now the last equivalent formulation, which is often referred to optional stopping, so it tells you for all stopping times, tau have that the stop process, so x tau, right, which is just given by the process stopped at time and the minimum, so the process at time tau minimum t, then we run over time as before, is an FT martingale. Okay, so these are the four equivalent statements which I want to prove now. Wait. Briefly. Okay. Let's come to the proof. Okay, first thing, well, we want to show that the first property implies the second one. So what does it mean? Just to recall it. So if I have a martingale, then for all stopping time, bounded stopping times, I know that the x tau is in L1 again, and the expected value of x tau is just given by x0, the expected value of x0. Okay, so how do you prove this? First, thing we know is that tau is a bounded stopping time. So what we know, there exists tau prime, which is, well, somehow between 0 and t. So right, I mean, what t might be infinity, otherwise we could take directly capital T. But since we allowed at the beginning for t to be infinity, we need some other tau t prime such that tau is less or equal than t prime. As I said, this exists thanks to the assumption that tau is bounded. And now we can define the following approximating sequence of the stopping time tau. So what we do is, well, we discrete time, we take our time interval, right? So we take our interval, which is the interval from 0 to t prime. We discretize it by duadic numbers. And then if for example, tau is, so many colors, so I should use them, is somewhere here, we take the next discretization power and say, this is my tau. Okay. So how do I write this mathematically, well, formally down? This means my stopping time tau n, which is my approximation of tau, is given by the sum from k to 1 to tau n. Now I will need to define my approximation. So S and K. I wanted to approximate with duadic numbers, so I take my interval, which has length tau t prime, and then I divide it by the 2 to the power n. Right? And then if I run now over k from k to 1, from k from 1 to 2 to the power n, well, I run through the whole interval 0 to t prime. Okay, so, and then I stop always at the later point here. So this is S k, an indicator function of Sn, k minus 1 to S and k, and depending on where tau is, I stop, right? So this is a sum which is, I mean, except one summand, all other summands are 0. Okay. And why do I want to choose the approximation? Because then I can rely on our discrete time results in order to get the statement. So what we would see here is tau n approximates tau from above, right? For almost all omega. Okay, almost surely, right? Everything. And if I look at the process where I take my process S and evaluate them only at the times S and K and run K from, say, 0 to the endpoint 2 to the power n, this is discrete time Martingale. Yeah. With respect to the filtration, so which filtration, we only need to have a discrete filtration, right? So you can also look at the filtration at the time S and K, again from K to 0 to S. Okay. So I have an approximation of my Martingale, of my stopping time, and well, this discretization also leads to discrete time Martingale. And the good thing is now I can apply the discrete time version of the optional sampling theorem, which you can find in the appendix. little sampling theorem. Right. If you haven't seen it, check out the appendix. So from this, we get two things. The first one is that x at time tau n is in L1. And if I apply my conditional expectation of t evaluated prime conditioned on the filtration up to tau n has exactly the property I want to show. So x at time tau n is equal to the expected value of tau t at time x at time t prime, given the information up to time tn. And this holds actually for all n. Okay. And now I know two things. Right? So what do we know? First, we know that this is, I look at the process tau n, the discrete process here, the discrete family of x tau n indexed now over the natural numbers, right? Because I'm running over all the discretization steps. This is a uniformly integral. Which you will see on one of the problem sheets. And that's nice. Since, okay, this is the first thing. The second thing is, since xt, and here we need the assumption that it's right continuous. So right continuous. We know that at least point-wise, if I approximate tau, I can approximate x tau by x tau n. So if this holds P almost surely, as n goes to infinity, this holds P almost surely. And this means it holds in probability as well. Okay, that's good. So if I take these two things, so let's call it, what is A and B? So A plus B tells me that we have also the L1 conversion. Okay. So hence, let's put everything together. So if I consider the expected value of x, the expected of x tau, and now what do we want to show? Let's recall it. So we want to show that the conditional, the expected value of x tau is equal to the condition like the expected value of x0. Right. So this is nothing else than okay. This is my L1 conversion. But now I can use the tau property, so I sneak in here. And well, this is where I can apply my discrete version, right? So I know what this is. So let me call this yellow star here, or yellows. Oh yeah, that looks okay. So I apply here my yellow star. If I find my yellow star, where's my, there it is. Right. And this is the martingale by property I equal to x. So exactly what we wanted to show. All right. So this was the first implication. And now we want to show that the second property should apply to the third one. So this is actually the most instruction one. So what we want to show is that if we have a bounded, if we have for every bounded stopping time tau, we know that x tau is in L1 and the expected value is given by x0, then the optimal sampling statement holds. So if I look at the two bounded stopping times, sigma and tau, which are ordered, so sigma is less or equal than tau, then x tau is again in L1. Okay, that's for free. And the conditional expectation of x tau given the sigma algebra at time sigma is equal to x sigma. Okay. Okay, for this purpose, what do you want to do? So we want to consider an event A in the sigma algebra x sigma. And what we want to show is what we want this to show this property here. So we want to show that and this is why we take an event out of this sigma algebra f sigma. And we said or introduced the following stopping time. Sigma tilde omega is given by sigma, the sigma itself if A is sigma is in A, and otherwise it's given by tau. So if you're in the complement of A. Okay, first claim, which I already said, we know that sigma tau is indeed the stopping time. Well, how can we see this? So what we want to show is that if I look at the event sigma tau being less or equal than t, this is an ft, right? So how do I see it? Well, I look at, I rewrite this event by sigma less than tau is intersected of A. Right? So actually what we have here is sigma tau, but then if you're on the set A, you know you can erase this. And this is, there's something missing, of course. So we need to look at the complement. So here we go. You see, prime. And here again, we can erase this because we are on the complement of A. So this means sigma tilde is just tau. So that's good. So here, since this is a stopping time, this is ft measurable. And here the same. This is ft measurable, right? Because the complement of st is in there as well. Right, by the definition of sigma right? And they are ordered, as you know. All right, so this is both in ft for all t. Okay, this is a reasonable stopping time. So when this is a stopping time, and now we can apply the second statement, because we also know that it's the sigma tau is a bounded stopping time, right? So and since tau and sigma were bounded stopping times, we know that this is bounded as well. So what we can do is we can apply the second claim to sigma tau and tau itself. And what do we get here? We get that x tau is equal to x0, right? This is equal to, so this is II, and this is II again, just apply to the sigma stopping time sigma tau. And now, well, this is nothing else than expected value of sigma x sigma conditioned, or I mean restricted to the set A, plus the expected value of t conditioned to tau. And here, this is why I left here bits of space. Okay, I can sneak in also the indicator function of A plus the indicator function of A complement, because if the sum just means it's equal to 1 on the whole space omega. But now I can rearrange this, because what you observe is we have, oh, this is an, sorry, this will be a complement, right? So you have here this term and this is the same, then they cancel out. So what we get here is that x times sigma multiplied with the indicator function of A is given by, right, equal to tau x times tau multiplied with the indicator function of A for all A. Okay, and this is what the definition, what we want of the stopping time. So by definition of conditional expectation follows. All right. Okay. And now we want to show that the third property implies the fourth one. So let's go back, see what we want to show. We want to show if for all bounded stopping times, we have that tau x tau is another one, and the conditional expectation here is the conditional expectation here is equal to x at time sigma. Then every stopped, perhaps if I look at the stop martingale here, this is always an ft martingale. Okay. Okay, what do we know? If we look at the stopping time, so any stopping time, this might be now an unbounded stopping time tau. But if we take it, take the minimum with respect with t, this is a bounded stopping time. So we can apply the third property, which tells us, well, x is in t. It's in L1, so it's good. I mean, so for every time L, we have already the L1 integrability, and x t is in tau t is in t. out. So now we just need to show that the stop process here is a martingale. Furthermore, right? So if we look again, let's take an A in Fs and S in T. So what do we have? And look at the process at time tau minimum t multiplied with the indicator function of the set A, right? I want to show that this is equal to x tau minimum s multiplied with the indicator function of A. Okay, so this is what we have to do. So let's do the right. So we have this. Now we sneak in again some indicator function. So I want to sneak in the indicator function that has tau. Yeah, this is okay. I sneaked in this new indicator function that s is less or equal than t, and this means I also need to add. So this is, of course, I threw away some events, so I have to add this event again. And the event I want to add is, well, the complementary one, which is s being bigger than t. Okay. And the good thing is now that if I look at this product here, which is just the indicator function of A, so this is right, being less than tau. The good thing is this is f tau minimum s measurable. Okay. And here I note the second one, that tau, if I look at this scenario, tau, this is a tau, not a t. This is a tau, right? This has the complementary one of this event, so this has to be a tau. We know that t is less, tau has to be less than s and less or equal than t. Okay, that's good to note. Right. So here we can sneak in the conditional expectation with respect to tau s, right? And since this is tau minimum s measurable, you can pull out this conditional expectation, the product of the two indicator functions. And here, well, we have noted that tau is strictly less than s, and t is bigger than s. So what we can here, we can rewrite the second expectation by replacing the t here by an s. Okay, and now we put everything together already. So here, this is a bounded stopping time. So here we can again apply E to say this here is nothing else than x times tau s, and then the indicator function are complementary events. So what do I get here? That's equal. Is the expected value of tau minimum s given A. Okay, so that's what we wanted to show. Okay, and now the last thing, okay, there's not much to do. If the stop processes are always martingale, then the process itself is a martingale. Just a short comment. So to verify X is in L1, the measurability, adapted, and X at time t conditioned on Fs is equal to Xs. You just need to choose the stopping time, which is tau. So you choose the stopping time tau in the fourth statement just to be t. That's it. Cool. Okay, so these are our equivalent characterization. Now I'd like to finish this video with some rather handy fundamental inequalities, which are Dupes inequalities, which you might have also learned in discrete time already in some other courses. Okay. So here I will drop the proof because, well, and the proof is rather straightforward. If you have the discrete one available, if you haven't, then okay, we need to prove the discrete one, which I don't want to redo. So again, let me, what the framework is, you have either, so my process xt has to be right continuous, right? This is in order to allow it to be approximated by discrete martingales. So here you have right continuous martingale or right continuous non-negative sub-martingale. And well, let's assume that t is strictly less than tau, infinity. Okay, then Dupe gives you two inequalities. The first one is called Dupe's maximal inequality. And this tells you that if I look at the event that my supremum, so my running maximum of the process from 0 to t of the process xt, and then I take the absolute values, it being bigger than some constant lambda, this is always less than 1 over lambda multiplied with the expected value of absolute values x at time t. This holds for all lambda being bigger than 0. Okay. So what you see is you can control in probability the running maximum of the martingale or non-negative sub-martingale with its terminal value, also the random variable at the terminal time t. Okay, that's the first one. And the second one is actually what we use even more, but you need usually this one to prove the other one, is what's called Dupe's LP inequality. P inequality. So let's assume P is being strictly being bigger than 1. And to have everything well defined, let's assume that xt is in LP. So what do we have then? You can, estimate the expected value of the running maximum, so the supremum from 0 to t of the process in absolute values to the power p by a constant, which is explicitly given by p divided by p minus 1 to the power p, and then again the expected value of the terminal time of the terminal run right xt to the power p. And again, so you can control the expected value of the running maximum, so the whole interval 0 tt of martingale, just by knowing the random variable at the terminal time. And this is rather helpful, or rather powerful, as we will see in the course. So as I said, I don't want to spell out the proof because it's straightforward if you have seen the discrete time versions of these inequalities, and then you just apply an approximation argument as we have done in the last proof. So that's rather simple. But if you haven't seen the discrete one, I mean, there's, okay, then it's anyway half proof. So what you need is to approximate the right continuous, and this is why we need to assume that it's the right continuous. Just a process. Yes, xt and plus apply the discrete time versions of Dupes inequalities. And that's it. I mean, so if you like, you can spell out the details yourself. I mean, as I said, not hard. You just need to look up the discrete time versions. All right. I hope you enjoyed the video, and see you hopefully in the next video.